Okay, we are going to look at section 12.2, and we're going to look at several problems and see if we can get you some help on this. I want to revisit our deacon example from the last section. And so remember we said we had 5 deacons. And so we're going to look at the difference between elections versus committees. Okay, so let's look at a specific example. So let's take our 5 deacons and in how many ways can you elect a chairman, vice chairman, and secretary from this group of deacons? Okay, so when you look at this, we are talking about electing. So this is an election, and we're looking at a chairman, vice chairman, and secretary. So that's 3 positions. So just for being, very simple here, let's just say we chose these 3 people, Mr. Smith, Jones, and Williams. Now, in an election, the order matters. And so let me explain what that means. So let's just say we let Mr. Smith be the chairman, Mr. Jones is the vice chairman, Mr. Williams is the secretary. Now, if that was chosen in that order, the reason why order matters is that the first one that we just did is different than if you said, okay, now Mr. Williams is the chairman and Mr. Smith is the vice chairman and Mr. Jones is the secretary. So in an election, order matters. Now, this is what we talked about in the last section when we were talking about permutations, and that's how we figured this out. So in a permutation, if you were answering this question, you would have 5 total deacons. We're going to pick 3 of them to be officers. You plug it into this formula and you end up getting 60 as your answer. So there's 60 different ways to elect those 3 positions from our group of 5 deacons. All right, now we're going to switch the problem up just a little bit. Let's go back to our 5 deacons. And now we're asking, how many ways can you form a committee of 3 members from this group? So, we Baptists, we like to form committees for everything. So we have our deacons. Now we're going to form some kind of subcommittee. So now a committee is different from electing positions. So we're going to pick 3 of these members to be on a committee. So let's use our same 3 guys, Smith, Jones, and Williams. Now they are going to make the members of the committee. Okay, now the order here does not matter in a committee because it really doesn't matter if you pick Smith, Jones, Williams, or Jones, Williams, Smith. It's still the same 3 people on a committee. So the order in which you pick them does not matter. Okay, so thankfully, the idea of committees should hopefully be familiar to you. Okay, now when the order does not matter, and you're talking about something like committees, then this is called a combination. Now, a combination is notated with a couple of different ways. This one is NCR. You still have the same. This is your total number of people, and this is how many that you're choosing from that total. All right. So when the order does not matter, you're going to use this formula. Looks very similar. The only difference is this part right here where it has R factorial at the beginning down here in the denominator. Now, let's look at plugging the numbers in. So we actually have, if you had your 5 deacons, we're going to form a committee. So we're going to use the combination of 3 people. We're going to plug our numbers in here. So 5 factorial is 120. 3 factorial is 6. And 5 minus 3 is 2. And 2 factorial is just 2. So when we simplify this, we get 10. because that's 120 on the top divided by 12 equals to 10. So there's really only 10 combinations of 3 people. Okay, so now keep all of that in mind. Okay, so when we look at permutations versus combinations, the important question here is, does the order in which you choose the elements make a difference? Okay, so if you answer that yes, it does make a difference, the order that you choose these elements, then you are looking at a permutation. And this is going to be like the election problem, where you are electing those different positions. But now if you ask this question and you answer no, then you are looking at a combination, and it's more like a committee problem. Okay, so those are your 2 big things. Now it is possible that it could be both of them. It could be both a permutation and a combination, or it could be neither of them. So we'll look at some of those examples here in a minute. Okay, now in the combination formula, which this is your new formula, we also have a different way in which we write this. We can write it using this notation of a parentheses with 8/4. And that means these 2 things are exactly the same. You have 8 total in the group. You're going to choose 4 of them. So you will see it written in the text both of these ways, and they mean the exact same thing. You use the same formula. So let's just do this example. We're going to use this formula, and we're going to plug in the numbers 8 factorial over 4 factorial times 8 minus 4 factorial. All right, when you do that, you can plug these numbers into your calculator. You get this 40,320 over 24 times 24. That's pretty simple to do in your calculator as well. You can simplify it again, and then you get that the answer is 70. Now that is not too difficult, but sometimes these numbers get really big. And so we'll look at that in just a second, and I'll show you kind of how you can use your calculator a little bit easier. Let's look at another example. A bag contains 15 pieces of candy. In how many ways can 7 pieces be selected? So again, the question here is, does order matter? We have 15 pieces of candy, 7 pieces are going to be selected. Does it matter which piece you pick first, which piece you pick second, and so on? So hopefully you got that the answer is no, it does not matter. So that means we can use our combination formula. Okay, so we're going to take 15 pieces total. We're going to choose 7 of them. You plug it into this calculator, or plug it into the formula, and this is what you get. Now, here is where, to me, writing this stuff out, 15 factorial is a big number. 7 factorial times 8 factorial is a big number. So I don't want to necessarily write all of those things out. So I would rather just plug this straight into my calculator. So let me show you how to do that. So here's our problem. And this is what I want to figure out the answer to. So I pulled up my scientific calculator on my computer again, and you are going to utilize, so here's your factorial button. So you already know how to use it, but you're going to use these parentheses buttons. And the reason why you have to have the parentheses is because of this denominator. So in this denominator, it's 7 factorial and 8 times 8 factorial. Those 2 things are kind of joined at the hip, and they are in the denominator, so you can't just separate them out. So you actually have to enter this in with big parentheses around this. So let me show you how that looks. So the first thing you would do on your calculator, you know how to do 15 factorial. You just type in 15, and then you hit the little factorial. And then you're going to hit divided by. So that's 15 factorial And then that line right there means that you're dividing. Now we're going to do to our denominator, and we need our denominator to stay together. So I'm going to use this parentheses. You use an open parentheses, which is this first one, and you put in 7 factorial times 8 factorial, and then you close your parentheses. So that tells me this whole thing right here is my denominator. Okay, then after you press equals, you get that this is 6,435. Now, it's very important that I want you to try this on your calculator, okay, because it does take a little bit of practice. So go back through, make sure that whenever you do this and you do it on your calculator, that you get this answer, 6,435. Okay. So that's just when you have big numbers, it's just easier to plug it into your calculator that way. All right, let's look at another problem. In how many ways can a full house of 3 kings and 2 twos be obtained? Okay, so this is in poker, and so they want to know how many different ways is this possible for you to get 3 kings and 2 twos. All right, so let's take a look at it. Let's just look at the 3 kings first. So how many different ways can you get 3 kings out of a deck of cards? Well, how many kings do you have? You have 4 kings in a standard deck of cards. And we want to choose 3 of them. Okay, so 4 kings, we're going to choose 3 of them. It does not matter the order in which you choose them. It doesn't matter. So we're going to use the combination formula. So when you plug in 4 kings, we're choosing 3 of them. You plug it into the formula. And then when you figure that out, there's actually 4 different ways to do it. Okay. So keep that in the back of your mind, because that's just the 3 kings part. Now let's talk about the twos. So we have the same thing. You have 4 twos, but you want to choose 2 of them. Okay, so here's another, the order doesn't matter. We're going to have 4 total twos, 1 from each suit. We're going to choose 2 of them. And when you plug this into the formula, you will get 6. All right, so how many ways to get 3 kings? There's 4 ways. How many ways to get 2 twos? There's 6 ways. Then when you have these 2 things and they are separate, you are going to multiply them together. And so the answer to this problem is 24. So there are 24 possible ways to get a full house. All right, so drawing a full house, there's 24 different ways. All right, so if that's confusing, play that little part back again. Okay, looking at another example. If a family has 6 children, how many ways can the family have 2 girls and 4 boys? So I've given you 6 babies here. And let's just look, kind of like the last problem, let's just look at the 2 girls. So what they're saying is out of these 6 children, 2 girls and 4 boys. But if I want to just look at the 2 girls, what they're saying, whenever some people get confused, how many ways can the family have 2 girls? Well, they could have girl, girl, then boy, 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 boy. But they could also have girl, boy, 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 boy. So we can do this, and so rather than having to count how many different ways that there are, let's talk about how we can do that mathematically. So in mathematically, if we will look at that, we have 6 children to begin with, and we are going to pick 2 girls. So we want to have 2 girls. We're going to plug this into our formula because the order does not matter. And so when we do that and you plug it into the formula, you get that there are 15 ways. There are 15 ways to get 2 girls. Now, what about these 4 boys? So what I want to kind of convince you of is that if you have 2 girls and you have 6 children, then that means the other 4 have to be boys. So the answer to this question is that there's only 15 ways to do this. So, but now I want to look at what if we rephrased this question and we reworked it from a different stance? What if instead we said, okay, well, is it going to be the same if we figured this problem out with 6 children and 4 boys? Well, it turns out that you do get the same answer. So you have 6 children, you're choosing, or you're going to have 4 boys, you plug it into the formula, and you also get 15. Now, this is not just coincidental. It turns out that there is a big, long fundamental theorem of counting and all of this. It's very, it uses Pascal's triangle. And if you'll just take my word for it, you'll probably thank me later. But if you want a real long explanation, it's actually in your textbook. So just in case you are wondering, so you can go back and check that out in this section. All right, so the answer to this problem is 15. Okay, now, a club with 20 members is to select a committee of 4 persons. And how many ways can this be done? All right, so let's look at our kind of key terms here. We know we have 20 members. You're choosing a committee of 4 persons. Remember that this committee is a keyword. So that means that you are going to do a combination. If you see that committee, then you just know you're going to do a combination. So let's take a look at it. If we go and we say, okay, well, I have 20 people total. I'm forming a committee of 4. Here is your combination formula. And we're going to simplify this. And I did put this straight into my calculator. And I got that there are 4,848 different combinations, different ways to select a committee of 4. Okay, so you might want to pause, work through that. Now let's kind of take a similar problem. What if you had a club with 20 members and they want to select 4 officers? The officers are president, vice president, secretary, treasurer. Now, in how many ways can this be done? So now again, you have your question, does order matter? And so in this case, you're not making a committee, you're actually electing 4 officers. Remember, that's the election keyword. So the election goes with a permutation. So you're going to use the permutation formula here. You have 20 members total. We have 4 different offices. And so when you plug it into the formula, you end up getting 20 factorial divided by 16 factorial. So it turns out there's actually 116,280 ways that you can select 4 officers. So again, you're welcome that you don't have to like come up with each individual way. I mean, we would be here forever. Okay, so just getting the answer here. All right, now, another example, how many different arrangements are there of the letters in the word geometry? Now, we're talking about arrangements. So I want us to think about what we know about permutations and combinations. We talk about the order mattering. Okay, in all of these problems, you have a total number and you are choosing or selecting a smaller number from that total. Now, this problem is different because we're not choosing anything. We're just rearranging letters. That's all we're doing. So we actually did some of these problems in the last section. If you look at the word geometry, so it's not an election, it's not a committee. You have 8 letters total. So 1, 2, 3, 4, 5, 6, 7, 8. All right, now the only repeating letter is E. There's 2 E's and there's 1 of every other letter. Okay, so if you remember when we did these examples, we said the total on the top, 8 factorial, because there's 8 letters. And then we took all of the distinct letters and we put them in the denominator. So there's 1 G, 2 E's, 1 O, 1 M, 1 E, 1 T. No, I'm sorry, 2 E's. So then it's T, R, and Y. Okay. Now, what's great about this whole denominator thing is all of these 1 factorial is just 1. So this is actually 1. 2 factorial is 2. So this is 1 times 2 times 1 times 1 times 1 times 1 times 1. So really, the whole denominator is just 2. So you get 8 factorial, 40,320 divided by 2. And the answer to this is that you have 20,160 arrangements, possible arrangements. Okay. Going to look at, maybe this is the last one, I can't quite remember. A club consists of 10 freshmen and 15 sophomores. In how many ways can they choose a president, vice president, treasurer, and secretary, along with an advisory committee of 4 people who are not officers? Okay, this is one of those problems that you're probably going to need to reread 2 or 3 times to really understand what they're talking about here. So I've underlined all of these keywords. So let's take a look at what we have. The first thing is we need to know how many is in the total group, okay? Because you always have to have a total number. So in this case, I want you to look at the problem and see if you can come up with how many people are in the big overall group that we are choosing from. Okay, so the key words: 10 freshmen, 15 sophomores. So the total group is 10 plus 15, which equals 25. Okay, now we know our total. So I'm going to take this in 2 different parts. The first part is I'm going to look at the elected officers: president, vice president, treasurer, and secretary. So hopefully now you know that election means permutation. So then we have the advisory committee. Okay, the advisory committee is separate. So let's first concentrate on the officers. So you have 4 officers. You're going to use a permutation. We have 25 total, and we're choosing 4 officers. And when you plug that into the permutation formula, you have 25 factorial divided by 21 factorial, and you get that there are 303,600 different ways to choose those 4 officers: president, vice president, treasurer, secretary. Now let's look at this advisory committee. So when we look at the committee, we again need to look at how many are we choosing from. Okay, so when we talk about how many are we choosing from, we had 25 total, but here's where this comes in. It says the advisory committee cannot be officers. So that means you have to hold this election thing first, and then you form your committee. So now after you've made your election, you don't have 25 people to choose from anymore. You have 4 less people. So you actually only have 21 to choose from. Okay, so because we have out of this 25, 4 of them became officers. Now we have 21 left, and we're going to make a committee of 4. If you remember that the committee means that you're going to use a combination. So this is your combination formula. I highly recommend that you put this in your calculator and you get 5,985. Now that's all great, but what's the answer to this problem? Because I have 2 answers here. So when you have 2 distinct answers, so this was the first answer, 303,600, 5,985. To get the total, you will say 303,600 times 5,985. When you do that, you get this astronomical big number, 1,817,046,000. Okay, so I know that was a lot. Let me see, and that is the last slide that I have. Okay, so I know that that was a whole lot. You may have to watch this over. To me, this is the one section in chapter 12 that kind of, it packs everything together, and there's a lot in it. So you're going to need to take your time as you work through this section. So let me know if you have any questions, and I'll be more than happy to help you with that.